All right, let's begin our discussion by looking at the basic circuit elements in circuits 1. And what we're going to find is everything we're going to do this semester is going to be divided into 5 basic elements. These are the 5 types of ideal elements in circuit analysis and circuit design. Voltage sources, current sources, resistors, inductors, and capacitors. And we're going to study all of those during this class. Now, a couple things to point out. First of all circuits, any circuit, it doesn't matter how complex, it doesn't matter what components it's made of, all circuits can be analyzed in terms of these 5 basic types of elements. So all circuits can be analyzed or simulated on a computer using these five classes, these 5 types. So all elements can be modeled this way, all circuit elements. So an integrated circuit, a transistor, any type of electronic component or electrical component can be modeled, broken down into these 5 basic sets of elements. And that's the foundation of circuit analysis and also the foundation of how we simulate circuits and predict how they're going to behave. So that's the first thing we want to keep in mind. Second is everything we need to learn about basic circuit analysis, all the principles, all the techniques, can be analyzed using the first 3, sources and resistors. So later on, we'll learn about inductors and capacitors, but we'll learn about those once we have learned all of the other techniques we need to know for this course. So we'll begin first just with these 3 sets of elements in order to learn all the techniques we're going to learn. Okay, so let's first discuss sources, voltage sources and current sources. What are those, and what's the difference between a voltage source versus a current source? Okay, before we start talking about a voltage source or a current source, I want a kind of broader definition first. And that definition is an electrical source. An electrical source is a device that can convert non-electric energy to electric energy and vice versa. So it can go back and forth. I can take a non-electric energy, turn it into electric energy, or electric energy and turn it into non-electric energy. there's a very simple example of an electrical source you guys are all familiar with because you probably carry one with you every day. And that is the rechargeable lithium-ion battery that's in probably all of your electronics. So a lithium-ion battery can be considered an electrical source. And what do we mean by that? Well, let's consider how we use one. First of all, a battery has discharge mode. Probably every one of you right now is carrying a cell phone with you, a smartphone. And if you think about it, there's a battery that's running that cell phone. So somewhere inside that cell phone, embedded inside of it, if you cracked it open, you would find a lithium-ion battery, which could be defined in terms of positive and negative terminals, or for the voltage of that battery. And that battery is supplying energy to the cell phone electronics. So that battery has negative power. The electronics in the cell phone have positive power. So current is flowing out of the positive terminal, okay? By passive sign convention, that makes this a negative power element. And as that current flows out, it flows into the cell phone. The cell phone will have a voltage across it, the electronics like so. It will have positive power. And what's happening in this battery is you have a chemical reaction. We have energy stored in a chemical form in that battery. And as that chemical reaction goes on in this battery, it generates electric current. So the non-electric energy stored in chemical form gets turned into electrical energy. Now, this is while you're using it during the day. The battery is discharging. Then what do? You go home at night, you go to bed, you plug your phone into the charger. And then you go into charge mode. While you're in charge mode, your charger now it starts generating power. It reverses the flow of current through the lithium-ion battery in your cell phone. So now the charger will have positive current flowing out of its positive terminal, which goes into the positive terminal of the battery. Now the battery has positive power. So in this case, as energy flows in, the chemical reaction is reversed and the battery charges. So in this case, we have electrical energy going to chemical energy. Whereas over here we had chemical energy turning into electrical energy. So we see this process every day, the idea of a rechargeable battery. So in this case, we have an electrical source for that battery. It can convert the energy both directions. In this case, the energy was negative. In this case, the energy was positive for the battery, according to the passive sign convention. Okay? So, looking at this, we see that an electrical source can have either positive or negative energy. Nothing changes about this battery. It just depends on how it's connected up. Is it connected to your cell phone? Is it operating your cell phone? Or is it being connected to the charger for the recharge? And so whether or not it's positive or negative power is not something that's inherent in the battery. It is a property of what the battery is connected to. So looking at this, voltage sources and current sources are both considered electrical sources. So voltage sources and current sources can have either positive or negative power in any given circuit, depending upon how they're connected up to other elements. And I point this out because many students, when they first start learning about circuits, will always assume it's a source. If it's a source, it must have negative power. It must be generating power. That's not true. Sources can also absorb power. They can also have positive power. How do you figure out which one it's doing? You have to learn how to analyze the circuit. So watch out for this. Don't make the mistake of thinking sources are always negative power. They're not. They can be positive too. All right, so first thing we wanted to get out of the way was that definition and resolve this fact about positive versus negative power for sources. Now let's talk about what voltage and current sources are, how we define them mathematically. And we're going to start with the idea of ideal sources. First is the ideal voltage source. The ideal voltage source is an element that maintains a specific quantity and polarity of voltage across it, regardless of the current flowing through it. So it doesn't matter what the quantity or what the direction of current is that flows through a voltage source. The voltage source will always have a specific voltage, a specific value, a specific polarity. Now, along the same lines is the ideal current source. An ideal current source maintains a specific current regardless of the quantity or polarity of the voltage across it. So these are the definitions we're going to use. This semester we're going to assume that all voltage and current sources are ideal. Now, along with these definitions of ideal sources, voltage sources and current sources can be subdivided into two different types. Voltage sources and current sources can be classified as independent or dependent. And you're going to become very familiar with both independent and dependent sources as you learn how to do circuit analysis. So what's the difference between these? Well, let's draw the symbols for voltage sources and current sources and look at the difference between independent versus dependent. An independent source has a fixed or constant value. It doesn't change. So for an example, an independent voltage source is drawn like this. We represent it as a circle. Notice the two terminals, and the positive and the negative show the polarity of the voltage source. So in this case, for example, I'll say this has a value of 1.2 volts positive to negative for that source. That's an independent source. The value and polarity, the quantity and the polarity are fixed according to that value. Now, then I have an independent current source. Once again, it's a circle, except in this case, I'm going to draw an arrow to illustrate the direction of current. And in this case, I'll say this is, for example, 10 microamps. Once again, two terminals to connect it to. It's an ideal circuit element, the direction and the quantity of the current. So these are independent sources with fixed values. Now, something I want to point out, and this is something you have to get used to because you're going to see this over and over. I can draw, in terms of orientation, I can draw these any way I want to. So for example, I could draw this on its side. I can flip this and draw this upside down. I can draw it diagonally. Orientation doesn't matter. You have to look and see how elements are connected together. And you'll see that a lot of problems in the books, in fact, a lot of just actual circuits, you're going to see elements drawn in all kinds of orientations. But you have to learn to look past the orientation. These elements are the same, they're just drawn at a different angle. Now, something else is I gave these positive values, but there's no reason why these have to be positive values. I could also, for example, specify a voltage and current source like so. Minus 6 volts or minus 2.1 amps. So the values, the quantities can be either positive or negative. So you have to look at both the quantities and the polarity and directions as defined like so. Okay? So these are independent sources. Then we have dependent sources. A dependent source means that the voltage or current of that source is a function of some other quantity, some other voltage or current in the circuit. A dependent source is drawn differently. Drawn like a diamond. Positive and negative for the voltage source. And once again, direction defined for the current source. So these are dependent sources. But the difference here is with these sources, the voltage or the current is going to be a function of something else in the circuit. So for example, in this case, Vs can be a function of some other voltage in the circuit. So I'm going to call that mu times Vx. So the value of the source is a function of this Vx, and this Vx is going to be defined someplace else in the circuit. So in this case, I call this a voltage-controlled voltage source. VCVS, voltage-controlled voltage source. Well, if you think about it, there's no reason why that voltage has to necessarily be defined by voltage. No, I can also define it as a current, in terms of a current. So in this case, I can define a different dependent source and say that Vs is equal to rho times Ix. So in this case, I've got some current Ix that is defining that voltage. I say this is a current-controlled voltage source, CCVS. Now, if I can do this with voltage sources, I can do the same thing with a current source. I can draw two different types of current sources. So in this case, I can say Ix is equal to alpha times Vx, so some multiplier times Vx. So Is is a function of Vx. This is a voltage-controlled current source, VCCS. Or Is may be a function of some other current in the circuit. It's equal to beta times Ix. In this case, it is a current-controlled current source. So you'll see these definitions, VCVS, CCVS, VCCS, CCCS. Whether it's a dependent source that's a voltage or current, and whether it's defined by a voltage or current. So 4 possible combinations. Now, if you think about this, you got to keep something in mind about the units. All right? Here, Vs is equal to mu times Vx. Clearly, mu has no units. It's simply a dimensionless quantity. It's a multiplier. Same thing over here. Is is equal to beta times Ix. Clearly, that is a dimensionless multiplier, but not for these two examples in the middle. Voltage is volts. Current is amps. So clearly, in order for this to work, for this row, units must be equal to volts per amp in order for the units to work out properly. Same thing over here. For this alpha, units must be equal to amps per volt in order to make the units work. Now, the reason I point this out is because when you go through and work these problems, you typically will not see these units expressed. So for example, you may see something like this. You'll see this type of dependent source. Here's a current source with a value of 0.5 times V1. Now obviously, in order for this to make sense, in order for that to be equal to amperes, then if that's volts, then this must be equal to amperes per volt. So those units are implied, but they'll never be explicitly stated. So watch out for that when you work problems. Okay? One other thing I should point out too, a very common mistake students will make. They will see, for example, something like this, a voltage-controlled current source. and they will treat it like a voltage source. And you ask why? But because you had 0.5 V1. But 0.5 V1 is not the voltage. This is a current source. 0.5 V1 is the value of the current flowing through it. So don't be confused by voltage-controlled current sources or current-controlled voltage sources. Common error people make when they're learning circuit analysis. All right? Now, once again, with dependent sources, just as with independent sources, orientation is irrelevant. I can draw these sideways, diagonally, upside down, it doesn't matter. You want to look and see how they're connected in a circuit, and we'll see lots of examples as you go through the semester where you're going to have to learn to think this way with these circuits. All right? Now, along with this, there's one other set of definitions. You'll often have sources that'll be referred to as active elements. What we mean by that is when sources are active elements, we mean that they are capable of continuously having negative power. They can continuously generate power, but they're not required to. So sources are active elements. Resistors, inductors, and capacitors, as we're going to see later on, are passive elements. And what do we mean by that? They can't generate power continuously. As we're going to see later on, inductors and capacitors can store and release power, but rather they can store and release energy, but they can't do it continuously. Sources can do it forever. They can be continuously having negative power. Passive elements cannot. So you'll see this active versus passive is going to be a term you're going to see as you go through the text and learn this material. So the final thing we want to look at is how we connect elements together. Turns out there's an interesting thing. If we start putting elements together, there are some ways that we can connect elements together that make no sense, no mathematical sense. So sources can be connected together. But not all combinations make physical or mathematical sense. Let's work some examples to see how this works. Let's look at some very simple circuits composed of a couple of elements. So for example, let's take two sources. And I'm going to take those two sources and I'm going to connect them together like so. So notice I've got two voltage sources and I'm going to pull their terminals out and I'm going to weld them together into a single point. I'm going to connect them together. And this is a 2-volt source and this is a 6-volt source. Now the question is, Is that a physically realizable circuit? Well, let's consider. What is this telling me? This says I've got 2 volts between these 2 points in the circuit as defined by that voltage source. This says I've got 6 volts, positive to negative, defined between these 2 points. There's only one problem. 2 is not equal to 6. This is mathematically the same as saying 2 is equal to 6. Not possible. So although I can draw this circuit and connect those 2 sources together, that's not a physically realizable circuit. It makes no mathematical sense. All right, what if I do this? What if I have a 2 amp and a 1 amp source like so? Okay, well in this case, the 2 amp source says 2 amps flows out in this direction and then returns through this terminal. This source says 1 amp flows out through this direction and returns through this terminal. There's only one problem. The current in these wires that I've connected these 2 sources together with has to be the same current. In other words, this is saying 2 amps in this direction is 1 amp that direction. Once again, that makes no sense. 2 amps is equal to 1. It makes no sense. Again, I've connected 2 sources together, but it's not physically realizable. They are contradicting each other in terms of their behavior. So once again, this isn't possible. But what if I do this? Is this physically realizable? Well, in this case, this source says we've got 10 volts. This source says we have 10 volts. They agree. 10 is equal to 10. That is a circuit you can build. That is a realizable circuit. What about over here? What if I do this? Is that a realizable circuit? Well, let's think about this. 2 amps flows out, 2 amps flows in, 2 amps flow out, 2 amps flow in. Do both of those sources agree? Yes, they both say that 2 amps is circulating around this loop through both of those elements. Therefore, that is a realizable circuit. So, not everything you draw or can put on a piece of paper makes mathematical sense any more than saying 1 is equal to 2 or 1 plus 1 is equal to 3. It has to be mathematically consistent. Let's throw this one in. What if I gave you this? What if I had an 8-volt source connected across a minus 1.5 amp current source? Is that physically realizable? And many people will look at that and knee-jerk reaction. They'll say, no, Dr. Holman, that makes no sense. That's a voltage source, that's a current source. On the contrary, a voltage source doesn't care what the current is that flows through it. So if I've got minus 1.5 volts going around this loop like so, due to that current source, that voltage source doesn't care one bit. The current source doesn't care what the voltage is across it. So if the voltage source says we've got 8 volts, positive and negative, as far as that current source is concerned, that's fine. It's perfectly happy having 8 volts across it. So in this case, it doesn't matter what the value of the current and voltage source are. This is a physically realizable circuit. And here you kind of see something that people begin to realize. Intuition can lead you astray. Many people will look at that and immediately say, no, Dr. Holman, that makes no sense. They can't be, that, you know, but no. Look at the mathematics. See if the mathematics are consistent. That's how you figure out, instead of just thinking about what is your intuition telling you, because your intuition very often will lead you astray. Okay? So, that's our introduction to sources. Next time, let's look at resistors.